Can you hear me? Is it on? Okay, cool. Well, my name is Lynsey. I'm a calls engineer at Slack, and I'm here to talk about, well, three things really. Like, first off, what is Slack, and how our video conferencing platform works in Slack. And the third, I want to share some lessons we learned in building our video conferencing tool in Slack. So first off, what is Slack? Slack is a messaging service, so you can send direct messages to people, you can have group conversations, you can have channel conversations around certain topics, and you can also have audio, video, screen sharing, and interactive screen sharing calls where you can share the same computer over the network. And that's the team that I work on. Now, in addition to providing a default calling application, we allow third-party integrations into Slack. So we allow calling applications like Hangouts, Zoom, Appear.in to integrate with our Slack. And you can see there that we have, you can start a call with Appear.in, for example, by just hitting the call button. So we've worked with different third-party integrations so that we can have more calling applications. And here the choice lies with the user. So instead of saying, hey, you have to use our calling application, we allow the user to have a choice. So in that regard, they have a default calling application when they get started right out of the box. And if that doesn't work for them, they can use Google Hangouts or they can use Zoom. And that works best for our user. So we want to do what's best for our user. A little bit about the timeline of how long it took to build a feature like this. It took about 2 years. Slack acquired a company called Screen Hero back in 2015. And after that, it took us about 2 years to get voice calls, video calls, screen sharing. And here we are today with interactive screen sharing as well. And so on the client side, Slack is built on Electron. It's a web app. So we can use Chromium's WebRTC. WebRTC is an open source software. It allows for real-time communication. So real-time audio, real-time video, real-time screen sharing. Electron has a lot of native features, which is really great for interactive screen sharing. So if you have two people that are sharing a screen that are interacting on the same computer, this is really great because we can render a transparent window and both users can interact on the same computer. So I'm going to go into a little bit of how this all works and some of the choices we made in building it. So let's talk about peer-to-peer. So peer-to-peer is one way of two users connecting their audio and video streams together. Peer-to-peer is really great because you have, in the first case on the top, you have two users connecting directly. So we can get the fastest possible time to get audio and video to those users. As we saw before, when we had like half a second of latency between this microphone and my mouth, that was really horrible, and we were all like, oh my gosh, like please stop talking because it's so bad. No, just kidding. But yeah, latency is really, really important. So that's one reason why we would have peer-to-peer. A downside with peer-to-peer is you can see when we have many connections, for example, 5 people, each person is sending their audio and video to each other person on the call. And that can get to be a lot of load on your uplink. So that's not so good. Another model is having something called a selective forwarding unit sit in the middle of two users that are connected on a call. So a selective forwarding unit, it forwards all the audio and video to the right person. So you have two people on a call, the server sits in the middle, and it just forwards audio and video between the two people. This works really well in large calling situations. So if you have a server in the middle and you have 5 people connected to it, each person only has to upload their audio and video once rather than 5 times. So if we compare side to side, our SFU model, each user is only uploading their audio and video once. In peer-to-peer, everyone has to send it to everybody. So we're reevaluating how we do this. So we started off with the SFU model because we wanted to grow for large group calls up to 15 people. But we realized that actually most people use one-to-one calls. Usually in Slack, it's just like, hey, I want to talk to you for a little bit. This is easy. Let's get this in real time, and then that's over. So we're doing kind of a hybrid model. What we do is we actually have peer-to-peer for one-to-one calls. So that's really, really fast. That's really, really good. And as more people join a call, we bring them onto the SFU so we don't bog down their uplink bandwidth. Another thing I want to talk about is scaling our calls around the world. So we have a lot of call servers around the world, like the US, Asia, Europe, Australia. And we use both AWS and Google, just in case one goes down. And we use a simple load balancing, so whoever is, whichever server is the least loaded, we send those users to the least loaded server in that region. One challenge with this, so when we use the one SFU model, there's a few challenges. So with load planning, we can't foresee how many people are going to join a call. Maybe we send a couple people to a server and they all grow to be really, really big calls. We can't predict the future and we can't see that happening. So with the single server model, this can be a detriment. Also, with one server for a call, it makes our deploys for our server code really, really long and difficult, because what we have to do is we have to push out a whole new fleet of servers with the new code, wait for all the calls to die on the old servers, and then route everyone to the new servers. And that can take over 24 hours. And in that 24-hour period, now we have 2 fleets of servers that we have to pay for, and extra bandwidth costs. Another downside to this one server model is the intercontinental latency. So if you have a user start a call in, say, the US, and other people join from the US, and you have one user join from Australia, their audio and video has to go from Australia to the US over this slow link. And that can be not as good. A better model is actually having 2 servers, each user connecting to the server closest to them for one call. And if we have a user in, say, Australia or Asia Pacific, they can connect to the server that's closest to them. That server can use the AWS or Google backbone, so it's kind of like the internet freeway. Things are very, very fast on there. They can send it to the server that's closest to the other users, and we can get less latency for our calls. With multi-server calls, we can have faster deploys, so we can migrate users to different calls mid their call. But this is something that's in the future that we're working on and we don't have yet. So another thing I'd like to talk about is serving our enterprise customers. So enterprise customers have a lot of needs that need to be met. So a little bit about this slide. We have our SFU, so our server that hosts all our calls, and then we have something called the turn server, which just routes packets and audio and video to our server. On the right, we have the signaling stream. So signaling is like, hey, I joined the call. Hey, I sent an emoji reaction on the call. Hey, I muted. That sort of thing. The media on the left is audio and video and screen sharing frames. Oh, now you can't see anything. OK, cool. So one thing enterprises do sometimes, this is not a good connection. One thing that enterprises do sometimes is they don't want to send out UDP. So UDP is this kind of fast way of sending packets, like audio and video, which is important to send it very, very fast. They don't want to send it out to every single possible UDP port on the internet. So they're like, hey, we only want to send it to port 22466, or just one port. So we can set their firewall, or we can say, hey, set your firewall so that you're only sending traffic to port 22466. And some of them seem happy with that. But some enterprises actually block UDP traffic, and that makes it harder to send media, because media usually needs to be sent on UDP. So what we've done with our turn server is we've actually opened it up to UDP or TCP. The TCP isn't going to be as fast, or maybe has a little bit more latency, but it works for them. So that's good. Another thing is that some enterprise customers, they said, hey, actually, we don't want to just send it on TCP. We want to send it on TCP only on port 443, which is kind of tricky, because in this model, we have 2 ports open. We have 22466, and we have port 443. So what do we do in this situation? we introduced HA proxy on the box. So our HA proxy gets both traffic for media and signaling, both on port 443. And then HA proxy is like, okay, is this media? Yep, okay, go to turn. Is this signaling? Okay, go to the SFU. And then we can serve all of our customers with all their firewall needs, which is really important. Something about our server. Our first server was from an open source Janus. We've actually switched off of that for a few reasons. So our Janus server, we forked and modified. There's a plugin architecture, and it didn't really suit our needs for certain things like Plan B and simulcast, which were going to optimize our users' experience, and it became really hard to add new features. So we actually built our own media server called Orca, and it's built on Elixir, which is an extension of Erlang. It's a functional programming language. And one thing I really love about Elixir is this idea of crash tolerance. So you can have a supervisor process. It's going to spin up more processes, like parent processes, and those parent processes are going to spin up more processes. If any of the processes in the bottom dies, it won't affect any of the other processes. So they can crash, and it's fine. So Elixir has this kind of philosophy of let it crash. If something's broken, just let it crash. It won't affect the rest of the server. Before, if we had something crash, it would bring down every single call on that server, and that was really horrible. So now, if something crashes, it only brings down one user instead of, say, 200 or 300 users. So we've isolated our problems by using Elixir. But Elixir is not all good. We noticed that Elixir was slow at doing the really number-heavy crunching of, say, encrypting and decrypting or active speaker detection. So we use a hybrid model. We use all the application logic in Elixir, and then we do all the heavy number crunching in C++. And that seems to work really well, actually. So I want to end with this. The Slack API for calls is not currently public. It's private, so we've just been working privately with companies or applications to get them working with Slack. But we do want to make the calling API public. So if you have thoughts, if you're like, hey, this would be really great if that API did this or that, come let us know. It'd be great to hear feedback. And that's it. Thank you.